Hello everyone, my name is Binyi Zhang. I'm from the Viterbi School of Engineering of University of Southern California. Today I'm going to introduce our work, Accurate, Low Latency, Efficient SAR Automatic Target Recognition on FPGA. So first of all, I want to introduce this task, SAR Automatic Target Recognition. SAR means Synthetic Aperture Radar, and is a kind of technology for remote sensing. For example, using this technique, we could get some SAR images for the target objects as shown in the bottom right figure. And so to recognize the target in the SAR is one of the most crucial and challenging issues in the SAR applications. And for the SAR automatic target recognition, there is a well-known dataset called MSTAR. It's a widely used benchmark for the SAR ATR. So in this paper, we use this dataset for evaluation. This dataset contains 10 classes of SAR vehicles, and each image has size of 128 and 128, and this dataset is publicly available in this link. So then I want to talk about challenges and motivations for this work. We find that traditional deep learning based method for the SAR automatic target recognition use the convolutional neural networks. However, the convolutional neural networks they use have a heavy convolutional operations, and they also develop very large signals to improve the accuracies for the SAR ATR. However, it needs two issues. First issue is that the signal models have high computation complexity. For example, uh, state-of-the-art signal models for the SAR ATR need nearly 1 to 6 billions floating point operation for inferences single SAR image. And this model also have large memory requirements because their models has millions of parameters. Also, they need a large memory space to store the intermediate results of the thin layers. So, due to these above challenges, those thin models are hard to be deployed on the resource-limited platforms such as small and micro satellites. So, based on that, we propose a graph neural network-based approach to address above issues. First of all, I want to talk about the graph neural network. Graph neural network is a type of machine learning model that has a stack of GN layers, and each graph neural network layer follows the aggregate and update paradigm. Um, this aggregate update paradigm has two steps. First step is that each vertex aggregates the features from neighbors, and in the update phase, each vertex features vector is transformed by a multi-layer perception. This is usually a single-layer MLP. So by recursively doing this, we can obtain the node embedding of those vertex. This node embedding is the vector representation for the vertex in the graph. So then I want to talk about the proposed approach in this paper. So in this paper, we proposed a gene-based model architecture co-design for the STAR ATR FPGA. First of all, this work consists of two parts. The first part is the gene model design, and we propose a novel GN model for the SAR ATR that has high accuracy and low computation complexity. And then we propose accelerator design that we develop a novel accelerator on the FPGA to efficiently execute the irregular computation patterns of various computation kernels in the GN model, such as the feature aggregation, feature transformation, and graph pooling. And our performance metrics to evaluate the work it has is accuracy, means the accuracies, classification accuracy on the M star dataset, and computation complexity means the total computation complexity for inference a single star image. And the number of parameters is the total number of parameters in the model, and the latency for inference star images, and also the energy consumption for the inference of star image. So our colleagues want to comprehensively achieve optimize those performance metrics. Mm, this slide shows the proposed GN model. So why we use, that is the question that why we use the GN model for the star ATR, because we find that in the star image, only a small part of the pixels belongs to the target, as you can see in this star image on the here. And for the star image, we can conveniently extract the pixels of target by applying a constant threshold. And then for those pixels of the target, we can construct a graph that sent to the GN model for classification. For the CNN network, we need to send the whole star images to the CNN network. So we can envision that using the GN model, we could potentially reduce a large amount of computations by just construct a graph from this pixels of target and send it to the GN model. So to do this, we first uh, we first have an input representation for the star image. We present a star image as a graph, which each pixels viewed as a vertex, and each pixels and or vertex is connected to the four neighbors, up, left, down, and right, with the edges. And for the features of vertex, we use the grayscale value of the pixels as the feature of the vertex. And then after we construct the graph from the star image, we send the graph to our proposed GN model. So our proposed GN model has three types of GN layer. The first is a GN layer. We used a graph stage layer for the GN layer can extract the graph related information from the input graph. And the polling layer is to downscale the input graph. For the polling layer, because our graph is built from the 2D image, so for the scale for the polling, we use the similar polling strategy as the scene layer. And then we propose the attention layer. Attention layer is to have the two parts. First is the channel attention, and the second is the spatial attention. Channel attention is try to focus on the important vertex features, and the spatial attention to focus on the important vertex. And this attention layer could help to improve the accuracy of the model. So using this proposed GN model, we can classify the target based on the graph structure information of the target, also the vertex feature information of the target. And then through our model design, we find that the proposed GN model achieves comparable accuracy as the state-of-the-art STM model with nearly um, 1%, only 1% computation cost, uh, because for the GN model we don't have the heavy convolution operation. We also just use the uh, we don't have the heavy convolutional operation as a CLM. And to further reduce the computation complexity of the proposed GN model, we propose two pruning techniques. The first is weight pruning. For the weight pruning, we trained GN model using the lasso regression. After the lasso regression, we set a threshold called I weight that that can prune the weight that has small absolute values. So this can not only reduce the computation complexity, but also reduce the size of the proposed model. And second pruning technique is input pruning, because as I introduced, in the SAR image, most pixels outside of the target has negligible grayscale values. So we can set a threshold and prune the vertex that has small grayscale value. Um, by doing this, we only need the pixels of the target to build the input graph. And through the network pruning, the proposed GN model can achieve comparable accuracy with the state-of-the-art GN model with a very small computation cost and very small model size. However, after we build this GN model, we found there are challenges for execute the GN model on the processor, because the GN model has a uh, has various kind of computation kernels, such as feature aggregation, such as feature transformation. For the feature aggregation, involves the propagates the information within a graph. So it has very irregular computation pattern. Also has very irregular memory access pattern. For the feature transformation, usually is a dense matrix multiplication, but because of our weight pruning, the weight matrix can become sparse. So the feature transformation uh, becomes uh, dense sparse or sparse dense computations. And there are also some other kernels like graph pooling. So based on that, we first categorize those computation kernels into two classes. The first class of model is called vertex aggregation kernel. We call it VAK. Feature aggregation and graph pooling can be categorized into the vertex aggregation kernels. In vertex aggregation kernels, each vertex propagates its feature vector to the neighbors or within a local range. And the vertex aggregation model kernel can be mapped to the sparse dense matrix multiplication. For the vertex updating kernel, uh, there are several kinds of kernels can be categorized into this class, such as feature update, channel attention in the attention module, and the last MLP layers. So for the vertex updating kernel, is the feature vector of each vertex is multiplied by the weight matrix to obtain the updated feature vector. Uh, because of our weight pruning, the weight matrix have very high data sparsity, around 1% to 33% data density. So therefore, it can be also mapped to the sparse dense matrix multiplication. And then we uh, propose the hardware mapping techniques that could map the two types of kernels onto the hardware execution. Since both vertex aggregation kernel and vertex updating kernel can be mapped to the sparse dense matrix multiplication, and we propose to execute them using the well-known scatter-gather paradigm. In the scatter-gather paradigm, we use the edge-centric approach. So for every edge, we that has a source index, destination index, and weight, we let the edge to multiply it by its source vertex to generate an update. And then for each update, we let it to be gathered to its destination vertex. We find that both the feature aggregation kernel and vertex updating kernel can be executed using the scatter-gather paradigm. So this figure shows the details. Because of that, we are able to uh, implement a unified hardware architecture design that can execute the scatter-gather paradigm. So in this architecture, uh, this figure shows our architecture on an embedded FPGA. First, it consists of application processing units that need to process the input SAR images to a graph, and then is our hardware design on the programmable logic. This accelerator has several parts: the scatter unit, routing network, and gather unit. This scatter unit, routing network, and gather unit can perform the scatter-gather paradigm. For the routing network is to perform all-to-all data communication between the scatter unit and gather unit because we use the scatter-gather paradigm. And there's also it is also noted that the vertex aggregation kernel and vertex update kernel has different data layout. So we implement a matrix transformation unit to transform data layout to prepare the data layout for the next layer. And there are also two buffers. The input buffer to store the input vertex features, and the wait edge buffer to store the edge of the graph or the weight. Because for using our mapping technique, the weight matrix is very sparse, so we also represent the weight as a edge in a graph. So you can see the details in the paper. And for our model architecture core design, we implemented on the embedded FPGA platform Xilinx ZCU104, and the application processing unit we use a quad core ARM A53 processor that running at 1.3 gigahertz. And this is the configuration of the programmer logic. And we use the 8 scatter unit and 8 gather unit. And for each scatter unit and gather unit, you can process 16 data in parallel. And for the accelerator, it runs at 125 megahertz. And we compare our accelerator with the two state-of-the-art baseline platform. One is the CPU, and another is the GPU. So this table shows their configuration. We can see that the baseline CPU and baseline GPU has very high peak performance and advanced technology. And as we introduced in the second slide, we used the M-star dataset for evaluating the accuracy of the proposed design. So this M-star dataset contains of 10 classes of vehicles, and it has nearly 2,700 images for the testing set and 2,400 images for the testing set. And This is the evaluation result. Compared with the state-of-the-art STEM models, the proposed GN models can achieve very high accuracy, nearly uh, in nearly 99.1% accuracy on the M-star dataset that outperform many SIEM models. With that high accuracy, it only has very small computation complexity and also has very small model size, less than 1 megabit. And this is the comparison of latency. For comparison of latency, we set the best size to be 1, and the evaluation result shows that our core design is nearly uh, 15 times faster than the baseline CPU and 2.5 faster than the GPU. Um, and this figure shows that our detailed comparisons for each image in the M-star dataset, we, uh, we, we achieve for all the images, our FPGA accelerator is the fastest one. And because for different images, the input graph may have different size, so you can see the inference latency fluctuate with the input images. And we also try to show the impact of our model design. And so we execute the baseline signal models on the Xilinx DPU, which is a state-of-the-art accelerator for the CNN. So we implement baseline CNN models on Xilinx DPU, and we implement our proposed model on our proposed design. Uh, Both the Xilinx DPU and our proposed design are implemented on the ZCU 104 embedded platform. And it shows that on the same FPGA platform, the proposed model is about 100 faster than the same model on the DPU, which shows that for the same target platform, our model could run faster. And we also evaluate energy efficiency of proposed approach to measure the power consumption on the CPU platform. Because we used AMD CPU, we could measure the power consumption using the tools called PowerTop to measure the energy consumption of the inference program. On the GPU platform, we measure the power consumption using the NVIDIA command tool. For our target FPGA platform, we use the external power parameter to measure its power consumption. So overall, our energy consumption is nearly 60 times more energy efficient than the DPU, and is nearly 40 times more energy efficient than the GPU, which shows that our design is very efficient for the SAR ATR tasks. So then I want to make a conclusion for our paper. So in this paper, we propose a novel model architecture co-design for the SAR ATR on the FPGA. Compared with the state-of-the-art CNN model, the proposed GN model achieves a comparable high accuracy, nearly 99.1% on the M-star dataset, with very small computation complexity and also very small model size. And the proposed accelerator on the embedded FPGA is 14.8 times and 2.5 times has lower latency than state-of-the-art CPU and GPU, and is more than 40 times more energy efficient than the state-of-art CPU and GPU. So to conclude, um, our paper proposed the accurate, low latency efficient SAR ATR gene-based model architectural designs on the embedded FPGA platform. So this work is uh, supported by the National Science Foundation, also the DEFCON Army Research Lab. And if you have any questions, please contact me through this email. Thank you for the listening.